There's this language that's kind of like a ghost in the machine of our modern world. It's called C. And it's basically the invisible architecture holding up pretty much all the tech we rely on every single day.
So you might be asking, why should we even care about a language that's, over 50 years old now? Well, because understanding C, it's not just about programming these days. It's really about peeling back the layers and getting to see how computers actually work, at a super deep, fundamental level. Just think about it. Your phone, your web browser, the OS on your laptop. C is in all of them. It's the silent, super high-performance engine just humming away under the hood. Seriously, you're using it right now, but you just can't see.
Okay, so let's dig into that foundation, this whole world that was basically built on C. The story kicks off at the legendary Bell Labs way back in the early 1970s. A programmer, Dennis Ritchie, he created C for one very specific and, frankly, monumental task: to build the entire Unix operating system from the ground up.
So what was it about C that made it the perfect tool for that job? Well, for one, it was built for pure, raw performance. It gave programmers direct, low-level access to the computer's memory, which is how you make things lightning fast. And that's what made it absolutely ideal for system programming, the code that's got to talk directly to the hardware. Its whole design was so influential that its syntax, it became the blueprint for languages that came later, like C++, Java, and even Python. And maybe the best part? It was portable. You could write code on one machine, and with minimal changes, it would run almost anywhere. A total game changer.
But how does that actually happen? How does this powerful code, which, remember, starts as just a simple text file, turn into something the machine can actually understand and execute? Well, that process, it's a really fascinating journey from our human world deep into the computers. So it all kicks off with something super simple, right? Like the classic Hello World program. At this point, it's just text that you or I can read. But for a computer to get it, that text has to go on a journey through 4 really crucial stages: pre-processing, compilation, assembly, and linking. You can kind of think of it like a translation pipeline, taking it from our language straight into the machines. And each step in that pipeline takes the code one step further away from human language and one step closer to the hardware. First, the preprocessor just cleans up the source code. Then, the compiler translates that into low-level assembly code. The assembler takes that and turns it into raw machine code. We're talking the actual ones and zeros now. And finally, the linker pulls it all together, bundling it into a single, ready-to-run executable program. Every single step gets us closer and closer to the metal. All right, so what's the secret sauce here? What's the ingredient that gives GPT all this power? What makes it so incredibly fast, but also, at times, kind of dangerous? Well, it all boils down to one legendary and, notorious feature: pointers. So, what in the world is a pointer? Well, it's a special kind of variable. But instead of holding the data itself, like the number 10 or the word hello, it holds the memory address of where that data is stored. The address book analogy is perfect. It doesn't hold the person. It just tells you exactly where to go to find them. And using them is like a simple 3-step dance. First, you've got your data sitting in a variable. Easy enough. Then you create a pointer and use the little ampersand symbol to get that variable's address. And finally, whenever you need that data, you just use the asterisk symbol to follow that address and grab whatever's inside. It's literally like having a direct key to any location in the computer's memory. And that right there is the core of it all. This direct, unfiltered access to memory is C's superpower. There's no middleman, no safety layer. The code is talking directly to the hardware. And that's precisely what makes it so unbelievably fast and efficient. But of course, with that kind of power comes, shall we say, enormous responsibility. Because if you're the one holding the keys to every single location in memory, well, you are now 100% responsible for managing it. You see, in C, memory kind of comes in 2 flavors. First, you've got the stack. It's automatic, it's safe, it's easy, it handles all the temporary stuff for you. But then there's the heap. And that's a big, open pool of memory that you have to manage all by yourself.
It's super powerful. You request a chunk of it with a command called malloc, but, and this is the part you absolutely cannot forget, you are responsible for giving it back with free when you're done.
So how many safety nets does C give you if you forget to do that? The answer is a big fat 0. Nada, zilch. C gives you no warnings, no help, nothing. It just trusts the programmer completely. And when that trust is misplaced, oh boy, that's when you get catastrophes. Forgetting to free memory? That's a memory leak. Your program just slowly, silently eats up all the computer's resources. What about using memory after you've freed it? That's a dangling pointer. It's like trying to unlock a storage unit after you've already given back the key. Total disaster. And then there's the infamous buffer overflow, a huge security risk. That's when you rent a small locker, but try to stuff way, way too much into it, and your stuff spills out and corrupts all the lockers next to it.
So after all that, all this power and all this peril, what is C's place in the world today? Well, it turns out its legacy is, and I'm not exaggerating here, nothing short of the DNA of modern programming.
I mean, you can literally trace its influence through the decades. It's born in the 70s to build Unix. By the 80s, it evolves into its successor, C++. Then you hit the 90s, and suddenly new languages like Java and Python are adopting its syntax. You know, the curly braces, the general structure, which made the C style of coding familiar to millions of programmers. And right up to today, it's still the absolute bedrock of our most critical software.
Yeah, C's role today is crystal clear. You use it wherever performance is absolutely, positively non-negotiable. The core of operating systems like Windows and Linux? Yep, that's C. Those tiny little computers inside your car, your microwave, even your smartwatch, they're all running on C. And the engines powering blockbuster video games and massive scientific simulations? You guessed it, that's the world of C and its direct descendant, C++.
Look, it really can't be overstated. C's core ideas about how language should look, how it should feel, how it should operate, they are so deeply embedded in computer science that its influence on modern programming is just immense. It truly is the grandparent of almost every single language you might use today. And all of this brings us to one final big question. I mean, today we have all these languages that are simpler, they're safer, they manage memory for you, and they protect you from making these exact kinds of mistakes. So you really have to wonder, in our modern age, is wielding C's raw, unfiltered power still worth the risk?